This is the first video for this class, and before I get started into our topic for this video, I would like to mention that while I make these from scratch, I'm doing my best to keep them interesting and relevant. I will try and keep them brief as well, but hopefully I'll improve and they'll get a little more fancy as time goes by, but I'm certainly open to any suggestions you may have. For this video in particular, video number 1 for Unit 5, we are going to review some concepts of gas stoichiometry. To work stoichiometry problems with gases, it is important to understand some constants and mole relationships. One concept is molar volume. 1 mole of an ideal gas at standard temperature and pressure takes up exactly 22.42 liters of volume. The identity of the gas is not really important here, but the temperature and the pressure most definitely is. Standard temperature and pressure, or STP, is 0 degrees Celsius, which is also 273 Kelvin, and a pressure of 1 atmosphere. Again, at these conditions, an ideal gas will always have a volume of 22.42 liters. This relationship can be used as a conversion factor in our calculations. I will work through a simple example problem as a review. This is number 11 in your example packet and is worked out in your textbook step by step on page 195. The problem says, a sample of nitrogen gas has a volume of 1.75 liters at STP. How many moles of nitrogen are present? This is a dimensional analysis problem. You may want to go ahead and pause the video and try this one on your own. This is really a simple setup. Starting with 1.75 liters of nitrogen, you should use the molar volume relationship we just talked about to go from liters to moles. The final answer is 7.81 times 10 to the negative second moles, with 3 significant figures. Let's try another one that is a little more involved. This is example problem number 12 from your example packet and is worked out on page 195. Quicklime, or calcium oxide, is produced by the thermal decomposition of calcium carbonate. Calculate the volume of CO2 at STP produced from the decomposition of 152 grams of calcium carbonate by the following reaction. Again, I encourage you to try this problem on your own and pause the video. 152 grams of calcium carbonate can be converted to moles, and then the mole ratio between calcium carbonate and CO2 can be used to convert to the final product, CO2. Then the molar volume relationship can be used as a conversion factor. You should get a final answer of 34.1 liters of carbon dioxide. But sometimes gas stoichiometry problems are not at STP and are a little more involved. I'm going to show you 2 more examples of gas stoichiometry problems before I end this video. This is example problem number 13 from page 196. A sample of methane gas having a volume of 2.80 liters at 25 degrees and 1.65 atmospheres was mixed with a sample of oxygen gas having a volume of 35 liters and 31 degrees and 1.25 atmospheres. The mixture was then ignited to form carbon dioxide and water. Calculate the volume of carbon dioxide formed at a pressure of 2.5 atmospheres and a temperature of 125 Celsius. Now this problem had a lot of data in it, so I've pulled out all of the important information in this problem and put it on this slide. You should pause the video and try to work through this problem. If you still need help, follow along or look at the book, but you really should try and get this one done on your own. You should be able to do these type of problems. If you look at this one, enough information is given on both reactants to calculate moles with the ideal gas equation. Since quantities are given on both reactants, we also know that this is a limiting reactant problem. I know how much that excites some of you. But since this problem is asking about a product, we should write the reaction so as to figure out the mole ratios between the reactants and the products. Once moles are calculated for both methane and oxygen, both need to be converted to CO2 to find the limiting reactant. In this case, methane is limiting. Now keep in mind you cannot determine which is limiting until you've actually used the mole ratios to go into the product. So a balanced chemical reaction is absolutely crucial for this. Once the moles of CO2 are found from the mole ratios, the volume then can be determined using the ideal gas equation from the limiting reactant. The final volume of carbon dioxide should be 2.47 liters. One other use of the ideal gas law is calculating the molar mass of a gas using its density. We are going to use two concepts we've discussed before and combine them. We know that we can solve for the moles of a substance by taking the mass of the substance and dividing that mass by the molar mass of that substance. So look at the formula again. Moles are equal to the grams of the gas divided by the molar mass. Okay, if we take this relationship between mass and molar mass and substitute it back into the ideal gas law equation, we end up with mass over volume, which we already know is equal to density. Therefore, with a little rearrangement, molar mass can be set equal to density times the constant R, temperature in Kelvin, divided by pressure. This combination of equations is pretty handy. It is not necessary that you memorize it. Any of the problems that use this combination can also be worked out independently using the other two equations. And I will show you how to do that in the next problem with both approaches. So this is the last example problem for this video. Example problem number 14 is from page 198 in your textbook. The density of a gas was measured at 1.50 atmospheres and 27 degrees Celsius and was found to have a density of 1.95 grams per liter. Calculate the molar mass of this gas. To find the molar mass of a gas, we need to know the mass of the sample and how many moles are in that sample. Let me say that again. To find the molar mass of any gas, we need to know two things: the mass of the sample and how many moles are in that sample. We can use the equation that we just discussed, molar mass equals density times R times temperature divided by pressure, to solve this, but there is another way worth mentioning, just in case you don't remember the combined equation. Since density is given in this problem, we know the exact mass of 1 liter of gas. And assuming we only have 1 liter, we have enough information given to use the ideal gas equation, assuming 1 liter. And we can solve for moles. That way we will know the mass of the 1 liter given by the density, and then we can solve for moles and know how many moles are in that sample. We use the ideal gas law, solve for moles, and take 1.95 and divide by those moles. Again, this problem can be solved by either approach, and both give the correct answer of 32 grams per mole. But there's one other thing I would like to mention here before wrapping up this video. It is not uncommon for a problem to give the above information, yet ask for the identity of the gas rather than its molar mass. Try to keep in mind that molar mass often leads to the identity of a gas in question. For example, the molar mass of the gas in this problem is 32 grams per mole, which would lead you to believe that this is most likely the common diatomic oxygen gas. Now, this question didn't ask for the identity of this gas, but finding molar mass will often solve that problem for you. It'll answer that question for you when they do ask for the identity. So this is the conclusion of our first video. Again, I try and keep them brief. Please come to class tomorrow and let me know if you have any questions.